Here. Find two positive numbers whose product is 100 and whose sum is as small as possible. All right, so have you seen this problem in class?
Nope.
Okay, so we're going to call x the first number and y the second. So their product is 100 and their sum, we're trying to optimize the sum. Okay, so there's the sum here is x plus y. Okay, so this is the sort of the standard setup here is you get two equations. One of them kind of is like, I don't know, has like the two variables you care about on a number. The other one is like the thing you're trying to optimize. So in general, your strategy here is to write two equations. The second thing you do is you almost always substitute. So we're going to solve this one for y. Okay, and then you substitute that over here in for x. So your sum is now x plus 100 over x. And then the third thing you do is take a derivative. So you write two equations, you substitute one equation into the other, then you take a derivative. S prime is 1 minus 100 over x squared. Okay. Then the fourth thing you do is you set this equal to 0. So that's 4, set equal to 0, and then you solve for x. Okay, so you got to solve this equation, solve for x. So to do that, you move this 100x squared over, you get 1 equals 100 over x squared equals 100. When you solve for x, you get x equals 10 or negative 10. Okay. Now, you're supposed to like show, in some classes, you're supposed to show that these actually are like the critical points that they produce a min or a max. Did your instructor mention anything to you about that?
Say it again.
Like in some classes, you have to actually show, like you have to either use the second derivative test or a sign chart. Did you get any indicator?
I don't remember anything about the sign chart.
Okay. How about the second derivative test?
Yeah, I've heard of that.
Okay. Well, because you got two numbers here. Now, the other thing, though, is that the question says find two positive numbers. So it can't be that one because that's negative. Right? So if x is 10, y is 100 over x, it's 100 over 10, which is 10. So those are your two numbers. X is 10, y is 10, and the sum is 10 plus 10, which is 20. It's about the most basic question you can get in optimization. Is there anything on that you'd like me to go through again?
Nope. Let's go with me.
I did not cover this. I'm gonna avoid it unless you tell me like for sure you want to do it, because there's a lot to get through here. It's not necessarily needed.
All right. Yeah, we can just keep going.
Okay, so number two. Find the dimensions of a rectangle with perimeter 100 meters, whose area is as large as possible. So here's your rectangle. X and Y. So the perimeter is 2x plus 2y. And the perimeter is 100. So 100 equals 2x plus 2y. So that's one equation. Then the optimization equation is for area. Area is equal to x times y. So now we've got equation 2. So you solve the non-optimization equation and substitute it into the other. So you get like this one here. If you divide everything by 2, you get x plus y equals 100. Make some more room here. You get x plus y equals 100, and then y equals 100 minus x. So you take that and you substitute it in here. So that becomes area equals x 100 minus X.
Okay. I'm seeing the concept of it,
Okay,
of solving these problems.
yeah. The problem is they get harder and like the step you eventually like, okay, I get that, but then you gotta like redo them a bunch of times to really understand them. So you know you're ready to take your derivative, but the way this is written, your derivative would be product rule. Right? Do you see that? It'd be first times second,
Yeah.
second. So you actually can multiply out. I mean, it's 100x minus x squared, and then the derivative is just power rule.
Right.
100 minus 2x. You set it equal to 0. You solve for x equals 50.
And then you plug it back in to solve for y.
Yeah. Now, because you only got one critical point, you can assume it's the right one. X plus y equals 100. So y also equals 50.
I guess like if like trying to decide what two equations to use for each problem,
Yes.
or one I have to work on the most.
Yes. Now the area is the last thing. The area here is x times y. It's 50 times 50. Yeah, be really careful here not to like forget to do that. And the units as well.
Wait, say that again. Sorry.
Sorry, so the units as well. Don't forget to put your units.
Oh, okay.
Don't forget, you know, area, like the final thing.
All right.
Like there actually is well, this one just says to find the dimension. Sometimes it says what is the area, determine the area. And so on. Okay. So let me try to help you more than just doing problems by this is one you should be able to do, but I'll help you walk through it. If you don't, I mean, if you remember from like taking SAT, you really should go back down to the question: what dimensions would require the least amount of fencing if no fencing is needed along the river? So you're trying to find the dimensions. You're trying to find X and Y. Okay. So read this and see if you can draw a picture for this scenario. And keep it simple, like really simple. No points for.
So it's just probably a rectangle with one side missing.
Yep, you get the water there maybe, and another rectangle here. I try to keep X always horizontal and Y vertical as much as possible.
Okay.
Okay. Now, what are two things you know about a rectangle that are as basic as possible?
I know the length times width is the area.
Right. So the area is X times Y, and the perimeter, which isn't really perimeter, is like fencing this time. What's the equation for fence? This is Y also.
It'd be 2y plus x.
2y plus x, yeah. So what are we trying to minimize, or maximize, area or fence?
Fencing.
Fencing. So that means we're going to need to do something with this equation over here. So do we know the area?
We do.
Yeah. So see how you can get the values and start kind of saying, okay, I can do this. Now I said before, you're going to write two equations, one equation, two equation. You're going to substitute the non-optimization equation into the other. So you need to either solve this for X or Y. In general, you solve it for Y. There might be an occasion where you solve for X. But
Okay,
Y,
so the non-optimized,
the one that you're not, yeah.
or wait, hang on. The optimized problem is the one you said you do the derivative of it.
Yeah, but not yet. Not till you get it in terms of just one derivative. Yeah.
Okay.
Yes. Yes.
Okay.
Yes. If you ever need me to just listen, tell me that. I'm not very good at that in this format.
There you go.
So your fencing is 2 times 180,000 over X plus X.
All right.
So I want you to take the derivative of that, please.
Okay.
let me know when you get that.
Okay, I just had to grab a piece of paper.
Okay.
Okay, I think I got it.
Okay, so the derivative is minus 360,000 over x squared plus 1.
Okay.
So you set this equal to 0. Okay, and you solve for x. And if it's not clear, you move one thing to one side, so you get 360,000 over x squared. You cross multiply, you get x squared equals 360,000. Then you take a square root. So
How's the bottom x squared?
this is just power rule. So this simplifies to 360,000 x to the minus 1 plus x. So
Right.
negative comes down front, subtract 1 gives you the power of 2.
Oh, okay. All right.
Okay. So then x is the square root of 360,000. So x is equal to plus or minus 600. Now it can't be the negative, because if we go back to what the context of this problem is, it's a length, right? So x is 600, and then y is 180,000 divided by 600. So I think it's like 300. Is that okay?
Yep.
Okay, 4, 5, 4, 6. Okay. Do you think like you're going to get one of these with either different numbers or the same numbers on your exam?
I'll probably get one of these. I don't think it had different numbers.
Okay. Yeah, because they're all different. Unfortunately, it's not like we can like replicate it.
One of these will probably be on there. Yeah.
Rectangular page containing 24 square inches of print. So rectangular page we know looks like this. The margins at the top and bottom. This one, okay, this is weird. I'm sorry. Yeah, this is one of those where as a student, I almost wanted to ask the teacher, like, is this the right picture? The print, I think this is the printed area, because we know there's like a border around pages, although we don't read very much anymore, but okay. So the margins at top and bottom are to be 1.5 inches. So the like, if you kind of see dimensioning, like this is 1.5 top and bottom. Okay, and then left and right is 1. Okay. What should the dimensions of the page be so that the least amount of paper is used? Okay. So this one's a little bit like, I kind of have to help here to like guide this problem. You want to choose X and Y in the interior, because that's the number that's given.
Yeah, let's do that.
So X times Y equals 24, because that's like this interior region. Okay, so the area of the big page of, I don't know, like the whole page is this X right here plus the left margin plus the right margin. So it's X plus 1 times Y plus 1.5 plus 1.5. Like this on the outside here is Y plus 3. This one along the bottom here is X plus 2. Is that okay? Is that clear?
Why here? Why is it Y plus 3 and X plus 2?
Well,
Oh, never mind. I got it. Yep.
yeah,
yep.
yeah.
Okay.
So the area of the page is X plus 2 times Y plus 3. This is the thing you're optimizing right here. This is the thing you're going to take the derivative of, but it's got both X and Y in it. So what do? You got to solve this equation, right? Which
Mhm.
variable are you going to solve it for? Which variable have we solved all of them for?
Hang on, this thing just popped up on my screen. All right. For X.
Why? We solved all of them for Y.
Okay.
Like you can solve for X, but like it's more, you know, Y is generally the one. So Y is 24 over X. So the area of the page, the thing that you're trying to optimize, is X plus 2 times 24 over X plus 3. And this is the thing you're going to take the derivative of.
Alrighty.
So now if you take the derivative of like, okay, let me make a moment here. Like you know how to do it from here. It's getting to here that's the hard part. It's the setup. The setup of this is what's hard. But once you get to here, it's just taking the derivative, setting it equal to 0, and you're done.
Uh-huh.
So the derivative of this, you can do product rule, but it's better to FOIL first.
Right.
It ends up being a little bit faster. So you end up getting 24 plus 3x plus 48 over x plus 6. That's an x.
Alrighty.
Okay, so now take a derivative of this line, a prime.
You want me to do it?
Yes.
Okay. Okay. Alrighty.
So it should be 3 minus 48 over x squared. And then you set that equal to 0 and solve for x. So why don't we just solve this for x? Take a minute or two for that.
All right. Alrighty.
So did you get x equals 4?
Yes.
Plus or minus 4? Good. Okay, so it's gotta be +4 because it's a piece of paper, but you gotta be careful here. Like, is that what they're really asking for? So are they asking for the interior dimensions or are they asking for the dimensions of the page? And I believe they're asking for the dimensions of the page. So you got to remember to add 4 plus 2.
Uh-huh.
Like that's part of your final answer. So your final answer is well, okay, X. Well, maybe we see the base of the page. Base is 4 plus 2, 6 inches. Okay.
Uh-huh.
And then Y is 24 over X. Okay, so that's going to be, that's X right there, as you know. So that's 6. And so the height is 6 plus 3, which is 9 inches.
That's the final answer.
That's your final answer.
Alrighty.
That's the area, you'd have to multiply.
All right.
It would not, it's common to, not give everything that's needed in these problems because you
Uh-huh.
do that. Okay. 4 feet of wire is to be used to form a square circle. I'm laughing because, I don't know why anybody would ever do this. But that's what they do. So this is your length of wire. This is your 4 feet, and you're going to produce a square and a circle out of it. Okay.
Uh-huh.
How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum total area? All right. So there's 4 feet of wire here. Okay. And we need the perimeter of the square. So the perimeter of the square is 4s or 4x. The perimeter of the circle is 2 pi r. You use x or it doesn't really matter. So this 4 is equal to 4s plus 2 pi r. Is that clear?
Right. Yep.
Okay. Now, what are we trying to maximize here in this problem? The total area. It says maximize the total area. So we now need the area of the square. The area of the square is s squared. The area of the circle is pi r squared. So we're trying to maximize the total area. So T is s squared plus pi r squared. So again, 2 equations, right? You got equation 1, you got equation 2. Okay.
Uh-huh.
You almost always solve one that you almost always solve this, put it in the other one. Now, this one's different. Doesn't have x, doesn't have y. Which do you solve for? So you got to think ahead. Like if you solve for s, you're putting it in here and squaring it. If you solve for r, you're putting it in here and squaring it. So it doesn't look like either really work that nicely. So it doesn't really, so I guess it doesn't really matter. I guess I might solve for s because it's slightly easier. It's 4 minus 2 pi r over 4 is s. But it's not that much. I mean, it's not like it's not the greatest thing in the world. I mean, it's still bad. So T is 4 minus 2 pi r over 4 all squared plus pi r squared. So you have an option here. You can either expand this because this is really a binomial and then take a derivative, or you can take a derivative as is and then go. I'm not even sure what's best. It's probably best here to actually simplify slightly. So 4 divided by 4 is 1 minus 1/2 pi r squared, and then just take a derivative like this. And the reason is because this 2 is power rule, And the chain rule inside here doesn't create anything weird. So it actually maybe is somewhat easier. Whereas multiplying by a binomial times a binomial is not too bad. You know, like 4 minus 2 pi r times 4 minus 2 pi r. That's not too bad, but it creates more terms, and you know, with pi's it could get messy. So the derivative is 2 times 1 minus 1/2 pi r. That's power rule, times the derivative of the inside function. Derivative 1 is 0. Derivative of this, because you're taking it with respect to r now. I should have made that more clear. R is the variable.
Okay.
And this, that's minus 1/2 pi plus derivative of this is 2 pi r. 2 times pi r, and power, it's power rule. Okay, I got a lot going on here. So let's do this slowly. So we're gonna multiply this 2 in, so you get 2 minus pi r times minus 1/2 pi plus 2 pi r. Okay, so when we multiply that in, we get negative pi for the first term plus 1/2 pi squared r plus 2 pi r here. And we're solving for r. So this might look, we're setting this equal to 0 and we're solving for r. So we're going to move the pi over, and then we're going to factor an r out of both of these. So it's r parentheses 1/2 pi squared plus 2 pi, and then you divide. So r equals pi over 1/2 pi squared plus 2 pi. Now a small cleanup here is to multiply the top and bottom by 2, because then you get rid of that fraction. So it equals 2 pi over pi squared plus 4 pi. But notice how they all have a pi in there. So you can divide everything by pi, and you get 2 over pi plus 4 for r. The question's asking for how much of the wire should be used for the square and how much should be used for the circle. So we need to go back and figure out S. S is this thing right here. So we go back and grab S. And we just substitute. So this is actually 1 minus 1/2 pi times r, and r is 2 over pi plus 4. So this 1/2 actually cancels that. So this equals 1 minus pi over pi plus 4. That's your S. Okay, and then it says how much should be used for the circle and how much should be used for the so the square is 4s. So it's 4 times this thing you just saw me do here. And then the circle is 2 pi r. So it's 2 pi times, and r was 2 over pi plus 4. So whatever, 4 pi over pi plus 4. And those are your 2 answers.
All right.
Generally, that one's not given on exams, but
Okay.
you asked, so you got it.
All right.
Would you like to do 6?
Yes.
All right. Are you familiar with WebAssign?
No.
Okay. All right. A solid is formed by adjoining 2 hemispheres to the ends of a right circular cylinder. Okay.
We don't have to do this one, to be honest.
Okay. Yeah, I was going to say I'm not even sure what to draw here, but yeah, let's move on.
Okay.
Okay, so you got some other problems here.
Yeah.
34 through 43. These look lovely. These are all sort of horrible, by the way.
I want to do 36,
Okay,
38, 39, or 38, 39, 40.
let's do 39 first because it's kind of like number one. So maybe it will make sense
Okay.
here when we do it.
Alrighty.
And you may have to give me that list again with numbers or throw it in the chat also.
Is 39 like a optimization?
Yes.
All right.
Okay, so find two positive integers. Okay, so X is your first and Y is your second, such that the sum of the first number and 4 times the second number is 1000. So see if you can write that is an equation, please.
Would it be X plus 4Y equals 1000?
So you have X plus 4Y is 1000. Now the product is as large as possible. So we're trying to maximize the product.
Okay.
The product is of the two numbers. What are the two numbers in terms of like what we have up here? Trying not to give it away. I'm trying not to give it away, but like, what is the equation? What, give this a shot here. What is the equation for product?
Probably X times Y.
Yes. Okay, good.
I thought way too hard about that.
Well, there's other things that you could have said that would not be correct. And I don't know. I didn't want to overly complicate it, but I wanted to make sure you understood. So you got your two equations here. I want you to solve this equation. Now, what did I said? Normally you solve for Y, but if you solve it for X, it's kind of nicer. So I might solve it for X here. Substitute that into here. Okay, so I want you to do that. I want you to take a derivative. I want you to set it equal to 0 and tell me the value of Y.
Okay.
How are you doing on that?
I got 100 over 8.
Okay. So what's that, like 12 and a half?
Something like that.
Okay. Yeah. Yeah, 12.5. Okay. So that's wonderful. But is that everything we want? Now it says two positive integers. So that doesn't work. Oh, it's 1000. Oops. That changes everything. So it's 1000 over 8, which is 125. Like, didn't work. Okay. So that's one of the numbers. What is the other number? You got to use this equation here for the second one.
What equation?
1000 minus 4y, or any of them that have both X and Y in it. Like you could use this one, you could use this one. It's like when you're solving systems back in the day, you go back and you use one or the other.
Yeah, what am I solving for?
X, the other number. So there's two integers, and you found one of them. The first is 125. What's the other?
Okay. So what I would do is go back to those original equations.
Yes.
X plus 4y equals 1000.
Yeah, or the
instead of solving
1000.
for X, solve for Y.
Well, you already have Y.
Oh, yeah, that's true.
That's what maybe is confusing when you do them. You don't solve for y. Like I said, you almost always do. The ones you just sent on this page are much harder than
Yeah.
like the ones you normally do, but that is the case here.
Alrighty.
Okay, so it should be like x is 500.
Yep.
Okay, so y is 125, x is 500. If it wanted the product, you'd have to multiply those together. It just says though to find the two positive integers. Okay, 30, you said maybe 38?
Yep.
Okay. All right. This is this one. I mean, this one is semi-doable for you because you probably know all the like intermediate pieces to it. So they're giving you this thing right here, but they don't tell you A and B. And based on A and B, it could be, you know, could look very different. But they give you a point. So let's use the point. Let's use what you have here. Y is 3, A times 1 cubed plus 1, I'm sorry, B times 1 squared. Okay, so 3 equals A plus B. So not great, but like it's something there. Okay, is that all right?
Yep.
Okay, now inflection point, what does that refer to?
Oh, that's a second derivative.
Second derivative. So we got to take two derivatives here. So take two derivatives of this for me, please.
All right. Of the first problem, right?
Yep.
Okay.
We don't know A and B yet. We just know that A plus B is 3, which is useless for now.
All right. Alrighty.
Okay, so you can check here if you'd like. This is your second derivative. Is that what you got?
Yep.
Great. Now, you set it equal to 0. And when you solve for x, because 1 is an inflection point, x equals 1 is an inflection point. Okay. You could solve this for x, but like this is telling you, this right here, this 1 is telling you that x equals 1. So 1 goes in for x.
Right.
Okay, so 6a plus 2b equals 0. And then we have this equation right here. It's like a system. You should be able to solve for a or b, and then the other one. Okay, so we'll do it together here. So let's just solve for b. B is equal to 3 minus a. We're going to put that in here. So we have 6a plus 2 times 3 minus a equals 0. We have 6a plus 6 minus 2a equals 0. And you get 4a equals negative 6, a equals negative 3 halves. And then b is 3 minus 3 halves, because that's a. Okay, so 3 is really like 6 halves plus 3 halves becomes 9 halves. So you get your values there. So in summary here, for this particular problem, you had to know that 1, 3 is on the curve. I know it says it's a point of inflection, but it's on the curve. Like that just means it switches concave down, concave up, or concave up, concave down, but it's on the curve. That's why we can use it right away. You had to know that inflection meant second derivative. So you take two derivatives. Then you had to know to put one into that derivative and get two equations, and then you were able to solve for A and B. Is that okay?
Yep.
All right. I forgot which ones you said next to look at.
Oh,
I know you said like 36 to start or something.
yeah, 36.
Okay. Okay, suppose that f is continuous from 0 to 4. F of 0 equals 1. And from 2 to 5, or the derivative is going from 2 to 5 for all x. Okay, so there's a lot there. Let's try to unpack that. F of 0 is 1. Okay, so there's my origin right there, and that's 0, 1. Okay, from 0 to 4, the derivative is 2 to 5. This means the following for sure. It means that it's always positive.
Uh-huh.
And that means this thing is increasing. The original function is increasing. Like, so if it starts here, it has to go up.
All right.
Okay. So they're saying, well, what? They're saying f of 4. So here's 1, 2, 3, 4. They're saying that f of 4, this is not to scale now, but f of 4 is somewhere between the y value of 9 and the y value of 21. And that's what they're trying to have you show, that f of 4 is somewhere in here. Okay, so let's assume so here's how this is like kind of a proofy thing. So assume f prime of x equals 2, because it says like at the least it's that.
Uh-huh.
Okay, so using a linear approximation, the linear approximation is f of a, whatever you're starting at, plus f prime of a times x minus a. Okay, and I'm gonna make this simple. This is f of 0 plus f prime of 0 times x minus 0. So f of 0 is 1, that's given. F prime of 0, we assume, is 2 times x minus 0. Okay, and this is just a linear approximation. So the linear approximation is 1 plus 2x. So now let's evaluate it at 4. 1 plus 2 times 4 is 9. See how it's that lower value there?
Mhm.
Okay. So now we do the same thing, but we assume it's the biggest slope that it could be. Basically, what this is telling you over here is we're trying to say, well, what if it's the smallest that it always is? What is the biggest that it always is? Like, what if it takes off really shallow? What if it takes off really steep? Okay, so the only thing that changes in this analysis that I just did is the derivative, like the slope. So this line right here is L of x equals 1 plus 5x, because that's the derivative there. So then you do L of 4, you get 1 plus 5 times 4, which is 21. Did you see like a linear approximation formula in your book?
No.
Okay.
We haven't done anything like a problem like that. So I don't know why he would assign it on the review.
Yeah, well, it probably liked it. So that looks good.
Let's see what Yep.
What next? We might have time for another problem.
I'm gonna see one more problem. If
Sure.
number 46 on the page I'm just sending you right now.
Okay.
Or is that like the one that was on the number 6?
Yeah, it's almost the same.
Okay, well, never mind.
The drawing of it is what I'm not sure of. Metal storage shape of right circuit. So the right circular cylinder is oh no, surmounted by a hemisphere. That's weird. I don't think you're gonna get that. What's surmounted mean?
We don't have to worry about it.
Okay, what maybe just some, if you got some any kind of lingering questions, there are things you want me to say, you know, that's true, you know, what you're saying, like that's right, anything like that.
None at the top of
No.
my head.
Okay. This is the hardest exam for a while in this class.
Yeah,
This is where it kind of gets the, you know, really is a tough one, but it eases up slightly after this.
I think after this one is I have my cumulative exam.
Okay.
Um,
If there's nothing else, thanks so much for scheduling.
all right.
Appreciate it. And I'll send you the notes here shortly, next few minutes.
All right, thank you.
You're welcome. Have a great night. Bye now.